times it by the molarity of the acid, which is unknown. That's the molarity of the acid. That should equal, so these are protons. So that side should equal the moles of the base, which is as simple as the volume in liter times the molarity. The volume of 15 milliliter, you divide 15 by 1,000. So you would get 0.015 liter times the molarity of the sodium oxide, which is 0.1005. And you find the molarity of the protons, the acid. Okay, so you divide both sides by 0.01. So based on that example, so this is not a true calculation. It's not true titration for time as of yet, but then just show you the what it takes to calculate the molarity of the unknown acid divided by 0.1 times 0.1005. Okay, and what's the molarity? All right,
Molarity should be 0.15.
Okay, so that's the molarity. So write down the answer with a proper sig fix. Okay, so looking at those numbers, so we have two sig fig. There is one in here, and there are four in here. So I'm gonna have to write down this as one sig fig. But then, if you want to carry these with that special case of 4 decimals, okay. So if you keep it with 0.1500. So typically, the limit is the limit of the volume. The volume tend to limit our way to report the answer as far as the molarity. So you lose. So you start with something exotic and extreme, accurately measured value, into reducing the amount or the precision of that number based on doing it yourself, doing it manually. But I'm going to convert that limitation into something that has no limit as far as nailing down those volumes. So instead of limiting ourselves, because that value is not really precise, okay, it is accurate, it is not precise. To make it precise, so following the rule of sig figs, so the 0.015 once again has 2 sig fig, that number has 4 sig fig, and both divided by 1 sig fig. That's the volume of 10 milliliter, which is 1 sig fig. So therefore, trimming down that value to say eventually, so limit it to only report the value of either 1.5 if you hold that 0 as precise, or if you assume 0 is not precise. So therefore, let's say if you measured 9 milliliter, for example, or not necessarily 10, or the value of 0.2, okay, which is you lost precision. So not to be limited to that situation. So we're going to turn the collection of the data using electronic. It'll open up all the possibilities. So we're going to zoom in and figure out the exact or the precise value of that acid inside that bottle to 4 decimals and more. Okay, versus doing it manually. Doing manually, you limit yourself for the precision. For that reason, so I've selected flipping this technique into electronic technique, and we'll see exactly what I'm doing later on. I'll be using electronic for tonight to maintain the precision of the calculations. All right, any question about how to approach the calculation? Very straightforward. Okay, which is the moles of the acid should equal the moles of the base, and how do you figure out the moles of either? So the volume in liter times the molarity of one component should equal the volume in liter times the molarity of the second component, equated to. and you solve for the unknown. So let me show you exactly the setup that will turn it into a very, very precise measurement. So now the setup requires the following. By the way, we all have that handout. So make sure you download that handout or have it ready nearby. Make sure we're going to follow that layout of the handout to the data. We're going to collect tonight trial 1 data. Okay. And then at the end, I'm going to supply you with trial 2 and trial 3 data later on. And you'll mimic exactly how to analyze trial 1, do it the same for trial 2 and 3, and then figure out the average of all these molars. At least, do we all have the data table? So go to that experiment 11 folder, click to open, and just download the data table.
Oh,
PDF
yeah.
file.
Yeah, I think that I would just be downloading it because for some reason I'm not seeing this sheet in my lab manual.
It's not in your lab manual.
Okay.
So the whole procedure has been improvised, as I said earlier, because we cannot report the molarity of the unknown acid high precision.
Okay.
We'll limit to either 1 or 2 significant figures, which is we'll trim down the precision, we'll defeat the purpose. Why have to do a titration to figure out the unknown?
Oh, yeah.
Versus using electronics. So we're going to use electronic, enhance the measurement of the data, and will give us a possibility to record the molarity with high precision, as high as 4 significant figures.
Oh, yeah.
Okay, but you need to follow the following procedure. Do you all have that table?
Oh, yeah. Yeah, so where should I find it in the Canvas shell?
So this is under the folder experiment 11. So click on experiment 11, and there's a PDF folder embedded inside the experiment 11. So
Okay.
click on assignment, experiment 11, under assignments.
PDF, yeah, I got that, yeah.
Okay, did you find it?
Yeah, let's see.
Okay.
File here. Okay. Acid-base titration data table.
Right. So
Got
make
that
sure you
one.
download it. We're going to follow that table to fill out all these missing parts.
Yeah.
So from that table, okay, so we can start filling out the following. So I want to titrate, as I said earlier, 10 milliliter of hydrochloric acid samples, but I need to measure it. So that requires measurement. So I need to deliver 10 milliliter, but I want to measure it. Okay, 10 milliliter of that unknown molarity of unknown acid, hydrochloric acid. I need to measure it exactly. And then the molarity of that acid. So we can fill out the one right before the last row, the molarity of hydrochloric acid. Okay, so I'm gonna keep them as unknown. The one above it, the molarity of the base, which is based on that bottle. So this is the bottle molarity. So write down the molarity of sodium oxide. So all these trials will have the same exact bottle. So it lies in the same exact sodium oxide with that same exact molarity.
Oh, yeah. Oh, yeah,
So
so
same exact bottle, same exact molarity.
yeah, and should this be under trial 1 or something?
Yeah, so we're gonna pursue, for tonight, we have a time enough to fill out and finish trial 1. It'll take a while to finish up trial 2 and 3, but I'm gonna supply those trial 2 and 3 separately once we're done trial 1. So we'll do trial 1, I'll show you exactly how to fully analyze trial 1, and then I'll supply trial 2 data and trial 3 data. From the data that are provided, follow the same as the calculation for trial 1. How do you figure out the molarity of the unknown acid? Do the same and figure out for trial 2 and trial 3 what should have been the molarity of the acid, of the unknown acid, combine them and calculate the average. Okay, so it should be straightforward.
Oh, yeah. And
so
I'm
do not
also
confuse
wondering,
yourself when I'm going to fold the packet. Yes.
okay, so I was just wondering if I should submit the table and the stuff from the lab manual for.
Oh, no, I would, yeah, do not confuse yourself. So I'll show you
Yeah, I'm just trying to see what I can submit for this assignment.
just that table. So there's a good amount of reading, good amount of Beckett. So the Beckett starts with page 86 and on and on. And lab report has 2 sheets, but then requires good amount of reading through the materials and all the steps and the procedure. So it'll take a while for me to show you all these steps for the procedure. We're gonna follow the same procedure, but then the data sheet, okay, we're not gonna submit that data sheet because these are meant for just manual, to do the titration manually using your hands. We're not gonna use our hands to titrate, we're gonna use electronic. Because using the hand titration, eventually gonna limit yourself of figuring out some volumes and report the molarity with precision versus using electronic. Okay, so I'll show you in a second how to do it. So we're not gonna follow the suggested lab report or the report sheet as in for experiment 11. Instead, we're replacing it with this data sheet. Okay, just one data sheet. So just submitting this data sheet once all the data are provided. So just follow up with the calculation, show me exactly the calculation and the average. Is that clear? We just follow one sheet for experiment 11. All right, now the procedure. So the procedure is following exactly the same. So I want to spend a little bit of time telling the procedure. So now titration requires a good amount of preparation. Lousy preparation, no results. Very delicate preparation, you're gonna gain good results. So the titration starts with the following technique. So I'll be using the stirring functionality of the blade. So I have a blade, which is a heater and stir, but I'll be using the stir technique. So I'll be using a magnet and a stir knob. There's a heater, there's a stir. I'll be using the stir to stir the solution for me instead of just manually shaking the solution every time I add acid to the base. I want to use the magnetic stir. It'll stir the solution for me automatically, so I relax. The second part, I want to use what's known as the, so I want to use a pH probe that will turn it into electronic. The pH probe is replacing the eye because I want to constantly looking at the solution and constantly looking at the indicator color changing from no color to pale pink. All right. So once I can identify like a faint pink color in the background of that solution, it means I achieved the endpoint and I'll stop the titration. But sometimes very difficult for us, okay, to figure out the hint of pink color or something that has pinkish in the background. Not really pink color. It has to be sort of a faint pink color that would disappear in 30 seconds. Very difficult to nail down. That pink color will disappear after showing for 30 seconds. But how to get that? Very difficult. So I'll be using the electronic. So this is replacing the eye and trying to identify the color. So this eye basically is just looking at the what's known as the acidity of the solution, the pH value of the solution. And the acidity of the solution is good enough to trace and measure what happened inside the solution. Since once you start with that solution, which is acidic, you dip it in, so it's gonna measure very low numbers for the acid. The acidity is gonna somehow lower upon addition of the base. So the acidity will decrease and the number is gonna spike. It's gonna increase. But I'll show you exactly what I mean. So we're gonna have followed the increasing of the pH value based on that probe and the solution up until I get a full plot, and then we're gonna analyze the plot to give us very accurate, very precise measurements. Okay, so this is our technique of flipping that. Instead of looking at the eye of the color of the solution, we're gonna utilize the pH probe to figure out the solution plot. All right, the next part is want to fill out the solution using a burette. So this is the glassware to be filled out with the sodium hydroxide. So before filling out, it's going to be a little bit messy. I'm not going to do all these steps because I've done them before we start the experiment. So I clean. So typically, so you start with, so here's a burette. If you notice the burette, I don't know if it shows on your side. So this burette has the following. So can you see the reading on the side? Can you see the reading? Do they look clear to you as far as the reason? What sort of numbers? And this is the amount. So this is where you want to add in your solution, your sodium oxide. Call that burette. Can you see those numbers? Can you see those numbers?
Yes.
Okay, so what do they say?
It's 10, let's see, 6, 7, 8.
All right. So this is the port, this is the beginning, this is the opening, and here's the other side, the valve. So the tip of it basically ends with, can you see those numbers? What values do you see?
$47, $48, $49.
Thank you. So they become extremely large down below, but very low. So it'll start, those markings start as 0. Up on top, there's a marking that would say 0. And down below, the marking will say 50. Okay, so these are upside down sort of glassware. We'll call them burette. So this has been cleaned before we start. So I've added good amount of tons of tap water first. Then I clean it with DI water, just small amount of DI water. Just rinse a little bit with a few milliliter of DI water, and then tilt it a couple times back and forth, rock it back and forth, and then open the valve and waste that water. So far it's been cleaned throughout by using just a combination of tap water and DI water and nothing else. No brushes, no soap, nothing else. If you use brushes or soap, you contaminate the inner walls. The inner walls are contaminated because no matter how clean that brush, eventually it's going to leave some debris. It's going to leave some contamination down here. So eventually, going to go back in cycles as far as how to get rid of them, clean them. They would not be clean. So no soap and no brushes. Well, how would you clean the inner walls of that burette? Just tap water and keep flushing it until forever. Okay, and then finalize that rinsing using DI water, small amount. Now it's been rinsed with the DI water, the last rinse, but the walls remain to be a little bit wet, so it has some kind of wetness of DI water. Okay, you don't see it, but then it remains to be maybe 1 or 2 drops of the water remains to be inside that glassware. We call that technique conditioning. So I want to condition this glassware in order to receive the new solution. So before I pour down my solution, that's my intention. I want to scoop 50 milliliter of that sodium oxide solution. I want to pour it, transfer it inside that glassware, that burette. But before, I want to condition the walls, the inner walls of that glassware to be able to receive that solution. Why? Because conditioning will maintain the molarity of that solution. Conditioning means start with the washing the inner walls with lots of tap water, then followed by DI water. The last rinse has to be with the same exact material, but a small amount. Maybe I'll show that part. So I'm going to add just a few milliliter. Okay, so maybe a small beaker. So what takes basically a small beaker, just make sure that beaker is clean. So the beaker itself needs to be rinsed.
Would you like some food here, or would you like me to leave it for you for later?
I'm gonna bring in some pipettes. So just small amount of sodium oxide and just wet the inner walls of that beaker. And all these solutions that I'm using initially are to be tossed away. So I'm going to just toss it away. Okay, so now I conditioned this beaker. So this beaker right now is conditioned. The walls of it are already wet with that solution. Now I'm ready to transfer a small amount. So just a few milliliter. And that one will go down inside that burette. So with the nozzle closed, so use the nozzle, close the nozzle. Then I want to add small amount. So just small amount. Okay, so what happened here? So notice small amount. So I'm going to just tilt it almost horizontal. I'm going to continue on rolling it back and forth until, so I want to continue on rolling it back and forth until the inner walls of the burette are completely wet and coated with the sodium hydroxide. Okay, so rock it back and forth until all the inner walls are wet with that solution. And then, so I'm going to waste that solution so it becomes wet, because whatever that droplets of water, it's been mixed with that added sodium oxide. So whatever that inside is diluted sodium oxide. So I'm going to open one part. So the nozzle is now cleaned. Close the nozzle and then waste the other part from the other opening. Okay, so in this way, the inner walls are completely coated with the sodium hydroxide. The inner walls of that container now is ready to receive the sodium hydroxide solution. Okay, so I'm going to mount it. And then I want to bring in small amount. So what takes basically just small amount. So this one is good enough because the size of that burette is 50 milliliter. So I want to add roughly 50 milliliter to that burette. Okay, don't bring in more. Let's say don't bring in sizable beaker that would say a couple hundreds and try to add it from here to that beaker. Once you expose that solution into the air, it's going to dry out. It's going to change the molarity. So to keep that molarity the same, the molarity says on it, that number is only true if you keep it capped and if you keep small amount of that bubble exposed to outside, which is fine. Within the time of titration, which is fine. But if you keep it outside for a long time, eventually vibration will kick in and the molarity will increase. Just be careful. So just small amount. Okay. And then I want to use a funnel. So I have a funnel. So once again, any glassware to be used, this funnel has been washed recently, so it remains to be a little bit wet. Eventually, once you try to bring in that liquid inside that funnel, it's going to drag all these droplets of water. It's going to dilute the sodium oxide. Whatever that number would not remain to be the same. So I want to get rid of all these solutions, which is basically water. So I want to bring in the waste container. I want to rinse them using that solution. So use that as a rinsing solution. Rinse all these droplets to make sure all that water is gone completely. So now all the inner walls of the glassware, so the inner walls of that burette is ready to receive that solution. I wetted the inner walls of that beaker. I wetted the inner walls of that funnel. I'm ready to transfer from place to place to place to place, maintain the same exact concentration. I don't want to change the concentration of that solution. That's the whole thing. So now I want to use that funnel and bring in the solution inside the burette. I need a little bit more. Add a little bit more. Good enough. So just about ready to titrate. Okay, so now, so make sure, so whatever that extra on this side, basically, try not to have any extra remaining outside for a long time, once again. So I waste it because whatever I'm gonna be leaving as extra, do not put it back in the bottle for the fear of changing the molarity. I'm gonna cap my bottle. So I'm gonna save the same molarity of that bottle until the end of the night. So all these glassware are empty. That's the one that keep transferring from that bottle onto that glassware onto the burette. So keep it empty, don't fill it. Now going back to that burette. So to finish the preparation of that burette, okay, so I'm gonna monitor the following. So it could be a little bit more difficult to see, but down that port of that valve, so that that valve has some kind of a droplets of air. There are buckets of air, a little bit difficult to see. So the only way to remove that bucket of air to open, close. I'm gonna open. Do you see it? There's one or two buckets of air somehow been wasted. You see them? Okay, so perhaps you didn't see them. But all that air possibly that would be occurring inside that valve are wasted. So I'm gonna go back and just add a little bit more of the base, just to make sure the value 0 is read inside the burette, since 0 is up on top and 50 is down here, down below. So this one is an upside down glassware. So I'm gonna add just enough until I see that 0. So bypass that 0. I just want to eyeball until it sees a 0 exactly. Okay. So I'm seeing the marking. So the level of that meniscus is at the 0 value. So I'm going to start with that initial volume inside the burette, which is 0. So just about ready for the titration. The rest of it is the following. Just show it on this side, perhaps. All right, so this end is ready. The burette is ready with my solution of sodium oxide. And I took care of all these air that happens to be trapped inside that nozzle. And the valve is closed, ready to go. All right, now I want to add 10 milliliter of the acid. So I have options. One option is to use an open beaker like this. So the beaker has a sizable mouth and it's sizable. I mean, the beaker says on it 250 milliliter sizable beaker, which is fine to titrate. Or Erlenmeyer flask. Okay, so Erlenmeyer flask is meant to titrate using manual shaking of the solution. So if you shook that solution quicker, eventually it's gonna sputter, and that sputtering will go back to the same solution versus a beaker. But since I'm not gonna touch that beaker, the beaker is for the purpose of just collecting solution without sputtering, because I'm gonna let that stirring functionality on that plate to operate. I'm not gonna take it and shake it manually this way. There's no chance for that solution to sputter or to fly off. Make sense? So I'll be using a beaker, much easier. So far what I have basically is a magnet inside that beaker, and I want to measure 10 milliliter of this unknown acid. I got unknown acid, I want to measure 10 milliliter. Now how to measure 10 milliliter of that unknown acid? So I'll be using the following technique. So I have this glassware, so it's a graduate cylinder. Okay, so I want to measure 10 milliliter. So the size of it is 10 milliliter. So I want to scoop out 10 milliliter of this unknown acid and put it inside the beaker. So my technique is the following. So I'll be using a pump. This is known as a pump. So I'm gonna connect it on this side, and then I want to scoop out. So easy acid. I'm gonna open the bottle. So deliver into that biped. So I'm gonna use my thumb to roll. So I'm using my thumb, and here's a bottle. Okay, so as I roll up, notice I'm gonna roll up the valve. There's some amount of acid already inside the tube. It's not enough, so I'm gonna just put it back and just roll it backward. And then just roll up again. Keep increasing until the volume is recorded as 10. Okay, a little bit more. So a third trial. Just about 10. Maybe one more. Okay, so I want to just make sure I'm at the 0. Okay, so this is the 0 measurement. So it is at 0 level. That's the 0 measurement. And down below is 10. So this is my 10 milliliter acid. So I'm going to scoop it out and deliver it inside the beaker. Okay, so the acid solution now is poured inside. So I'm going to go ahead and close that bottle. All right. So here's the 10 milliliter of that unknown molarity acid is inside. Now, for the sake of titration, so obviously the volume is not sufficient, barely covers the bottom. So I'm going to do one thing. I want to add water, which is fine. So I just want to add water, just make sure I have enough of volume to be able to see the things. Otherwise, the volume is so small, so tiny, it doesn't matter. So the volume to be added would not affect the amount of moles of the acid poured in. Okay, there's specific number of them found based on that unknown molarity and the measured amount, 10 milliliter. There's a specific number of moles of them locked in. That number would not change. For example, by analogy, let's say if we are 25, and if we're gathered into a lecture hall, sizable lecture hall, our number would be increased or decreased or remain to be the same, will be the same. So whether or not we squeeze inside a small classroom or a large lecture hall, our number remains to be 25, for example. The same as the number of moles of the acid. Whatever that number locked into that beaker based on that 10 milliliter measurement will remain to be the same. You can add enough of water, you can add an ocean of water. Their number of moles of the acid remains to be the same. That's the idea. So water would not factor in as far as changing anything. Okay, it just changed the volume, but would not change the moles of the acid. All right, to that water, which is so far it has 10 milliliter of the acid, I'm going to add 1 drop of phenolphthalein just to show some colors. So we call that an indicator. Phenolphthalein is suitable for this reaction of hydrochloric acid and sodium hydroxide. Not all reactions of neutralizing acid and base are suitable for this indicator. This indicator is sort of giving the hint using the visual. Let's say if I want to use the visual to figure out the endpoint, when just enough of adding base to the acid in such a way as I added enough of moles of the base to the initial amount of moles of the acid. When that occurs, when that happens, the indicator is going to say, it's going to flag to me, will say stop based on the color changing from no color to pink. It'll say stop, and the moles of the added base now matches and equal the moles of the acid to be reacted with. So the indicator is going to help me to flag the endpoint. It's going to say, well, you've added enough, therefore the stop. But since I'm not using the visual, I don't need it because I'm using electronic. Electronic operates in a different way. Electronic does not need the visual, does not need that phenolphthalein indicator. I'm gonna add it though, even though it's not needed. We don't need it. Okay, the purpose to add that indicator is to flag the color for us to say, stop, you've added enough of base to the acid, so therefore the titration is done and finished. It's not needed for tonight because I'm adding electronic. So I'm adding a pH probe inside a solution based on the acid plot is gonna give me an indication whether or not I achieved the endpoint. I've added enough base to the acid. I'm gonna add it still, but it's not needed, just to make the point. What you need basically is to add 1 drop. Okay, don't add so many of them. Just 1 drop is sufficient. And I'm ready to titrate. Okay. So first, I'm going to start the stir. So there's a stirring functionality on this end. So I'm going to add maybe 1 or 2 rotation. So just make sure the rotation. Can you see that rotation? So I guess the best of the best, if you have the background sort of showing exactly what's going on. So I guess I'm adding that feature, to have the background a little more whitish. So in this way, you'll be able to figure out that pink color development in the solution. Can you see that magnet rotating? So jack up the rotation a little bit. And now the solution is ready to be titrated. Okay, you see the setup? So I have the nozzle up on top, and I got my solution ready to go. Now, what remains, obviously, is how do you titrate this using electronic? Let me just bring it a little bit closer. So here's my electronic. Okay. That electronic is identified as pH probe. So I want to submerge it inside that solution, and I want to use the software to help me out figure out the endpoint. So I'm just cleaning the head of that pH probe. The head of that pH probe has a little bit a hemisphere, which is made out of microchannels at the bottom, very sensitive, and it has microchannels that would communicate between the solution outside and the solution inside. There's a solution inside. The communication between them, it'll configure itself into showing as voltages, into showing pH value, a little bit more roundabout as far as the numbers, but eventually the pH values is sensitive to what's known as acidity of that solution. As I'm adding more base, the acid value, the amount of proton will decrease up until they become neutral. It means the amount of added OH is similar to the amount of proton found initially in that solution. And sometimes you can add a little bit more to far exceed the amount of initial number of the moles of the proton. So that's the approach. So I want to keep adding enough of OHs up until I'll match the same number of the proton inside solution. And I want to exceed it a little bit. Okay, so let me dip in that probe inside. So I guess the best way as far as to handle that probe is to somehow, I need to come up with sort of a suspension. I want to suspend it a little bit. Let me just tape it, because I don't want to touch the, I don't want that probe to be touching the magnet. Yeah, it's gonna break it. I guess I can tape it. Okay. All right, is it clear as far as what's going on?
Yes.
So I have the pH probe submerged in the solution, and then I can add a little bit more liquid. Okay, so now it's barely touching, but I want to touch the solution a little bit more, so I can add some water. Okay, so now it's submerged fully inside the solution, and that glossy hemisphere is already submerged in the solution. That's what you want to start with. So that's the initial position of it. The next is to set up the software. So I want to set up the software. So software, so typically if we happen to be in the lab, so I give separate handout for the software, and I'll direct my students to use that software. So I'll provide those tiny computers or gadgets, Vernier gadgets, and in them the same software that you see here on a typical laptop or typical desktop, but then these are tiny gadgets called LabQuest, very tiny. So either way, either using the tiny gadgets screen or using like a software installed into a computer. So we're going to open what's known as folder 7A. That's a folder suitable for the titration. Once you open that folder, you're going to see the following screen. It says on it, acid-base titration. The x-axis are measurement of volume of sodium hydroxide added in milliliter. And the y value are the pH measurements, which is your plot, which is coming up. And here's a screen that shows the value so far in the solution. Notice the numbers are low. It means the solution is acid. Since you only added 10 milliliter of that unknown molarity, it has a good amount of protons. The reason why the pH value is low. That pH value is going to increase or will keep on increasing the minute you add hydroxide, sodium hydroxide, because the number of the protons available will be lower. As they become lower, the pH value of them becomes higher. They go opposite. The lower the proton, the higher the pH value, on until I added enough of them until a plot that would show the following typical shape of it. So maybe just I'll give you that shape of that would be a plot. So first the plot will start as straight line. There's a jump, and then it will be followed by a second straight line. So it'll be almost straight line, like slightly tilted upward with a slightly positive sloping. There'll be a jump once I approach the end point, which is I've added enough of base of the acid, beyond which, if you add a little bit more, it's going to generate a second plot, a second straight line. Okay, so I want to have that look of the plot of the pH on the y-axis versus the added volume of the sodium oxide on the x-axis. Okay, and I'm ready to add the sodium oxide. So let me start the software. So this software requires the following. So in here, so once I click on that dial, so there's a dial that says stop or collect. So I click on it, and there is something appears to be activated. So there's that dial, which is, so this is a keeper, what's known as a keep dial. That keep dial basically, it'll say the following. So here's the first measurement. Do you see that point? Can you see that point on the plot? So that's the first measurement, but then I haven't added anything. There's a value. What's the value of that pH in that solution? So the probe is measuring something inside the solution. What's the value of it? 2.21. But did I add anything? Not yet. Okay, so I'm going to go to that dial. So I'm going to go to that dial that says keep. I'm going to hit it. So here's a window pops up that will say, what's the amount of volume you've added based on that measurement? Well, that comes about automatically by itself. I haven't added anything yet. So I did not add anything, so 0. True? Because I didn't add anything. So I'm going to hit 0 and say OK. Now I'm ready to add a few milliliter, maybe 1 milliliter or 2 milliliter. I'll watch out if the pH values start to jump quickly. So first I want to approach it by adding slowly, maybe a milliliter, maybe 1/2, 2 milliliter, maybe 1 milliliter, maybe half a milliliter. I want to see the chance of increasing gradually that value. I don't want to jump quickly. Typically, once the pH value at around 5.5 to 6, it'll start to quickly jump. It'll jump between 6 to 11 by adding a single droplet. One droplet of the base, it'll shift that number from, let's say, 6 to 11 to 12. It's a sizable jump, so I'll watch out. So I'm going to drag that number up until somewhere around maybe 5, 5.5, and then I'll slow down as dropwise. So but first, I want to add maybe a sizable amount. Let me add a little bit. Have you noticed any colors occurring? Do you see those colors? Do you see those colors?
Is it blue?
Yeah, so there's a pink color developing when I've added the sodium oxide. So let's make the first measurement. So what's the volume I've added? So I'm going to read straight the volume. Let me add a full milliliter. Okay, so that's the first milliliter been added. So now the reading is at 1 milliliter. Okay, so watch for those numbers. Once those values stabilize and not moving, it means you're ready to collect or to keep those data. Okay, so you're ready to keep those data. Okay, 2.24. Okay, so let's keep those data. So keep, hit keep, and window pops up. So far, I've added 1 milliliter, so I'm going to write down 1. I've added 1 milliliter. Okay, I'll continue on adding. So here's my second point. Here's the first point hidden right on the y-axis. Here's my second point. Now I'm going to add the second 1 milliliter. So I'm going to slow down. So that nozzle, my hand is on that nozzle. I'm reading the second milliliter to be added. So open the nozzle carefully, add the second milliliter, and stop right there. Any changes? Have you noticed any changes about those values? Hardly, right? Okay, maybe slightly. All right, so let's start to increase slightly. 2.27 versus 2.24. Very, very minor changes. Okay, so if these numbers are stabilized, they're not moving, and within a minute you don't see them flickering tremendously, it means accept that value. So I'm going to keep that value. So far, the reading on that burette says 2.0 milliliter. So 2.0. So that's the reading. Okay, let me add the third milliliter. Okay, so I'm going to add a third milliliter. So one hand on the nozzle and deliver the third milliliter. Well, have you noticed the color?
Oh yeah. I noticed it slightly turned pink due to
Right.
some phenolphthalein in there.
So now that being color, if I'm sitting at the end point, it means the moles of the acid are equivalent to the moles of the base added. If you're sitting on that point, which is equivalent amount of acid with the equivalent amount of base, the pink color will stay in solution for 30 seconds. It'll keep appearing throughout the solution for 30 seconds, continue on appearing, and then somehow on its own, by itself, fades away and goes away after 30 seconds. That's the exact matching of the moles of the acid with the moles of the base. But if that pink color solution remains to be pinkish, it means you exceeded the addition of the base slightly. Okay, so what sort of changes occur to that pH? A little bit, maybe a little bit more. So start with 2.24 now, 2.36, very slight, like very, very minor. But I'm a little bit far from that danger zone, which is when the pH starts to coming close to the 6. Okay, I'll watch out. So I'm going to keep that value. So far, the number says 3 milliliter. Double check. So 3.0. So 3.0 milliliter. All right, so I'm going to add the fourth milliliter. Okay, so I've got a little more than 4. I'm at 4 I'm at 4.1. All right, but that pink color fades away. So that pink color should be showing all around the solution and should stay in solution for 3 seconds, but not yet there. But the duration of that pink color appearing, disappearing, start to get a little bit longer. So the time start to get a little bit longer and longer, and eventually the pink color will stay in solution for 30 seconds and longer. So I'm going to keep that measurement. So far the reading is 4.1 milliliter. So 4.10 and accept. Okay, let me add, so now I want to be careful. All right, so let me add half a milliliter. We're getting close to 5. Let me see if I can add until 5. What would be the damage? Okay, so right now is about 5. Okay, so far I've added 5 milliliter and still remains to be in a safe zone. Okay, so the numbers are not flickering to become stable. So I'm going to go ahead and just accept that value. So far I have 5.0. All right, I'll go ahead and add another milliliter. I want to keep an eye on that color. Okay, so now I'm slowly adding the sodium oxide. And here's the 6 milliliter. Let's stop right there. Okay, so yeah, I'm still far away from that 6, and the color did not stay, so I should be good. So I'm gonna keep that 6 milliliter. So far, I've added 6.00 milliliter. Let me add another milliliter. All right, just about 7. All right. Did we see what's going on? All right. Any questions so far about what I'm doing?
Okay, so on the graph here, just each dot represents the pH of every increasing milliliter of the phenolphthalein solution.
No, the phenolphthalein is just 1 drop. So that little indicator, I just added 1 drop to that solution just to show the visual, the pink color. So, and beyond that 1 drop, that's it. There's nothing to do with the phenolphthalein indicator. What remains here is I'm just keep adding the sodium hydroxide to the existing proton because I have acid in here in that beaker. I'm keep adding base to it through that burette.
Oh, and so the
Until
milliliters here.
the acid and the base are equivalent.
Oh, yeah.
Okay.
Yeah, so from what I'm seeing with every milliliter, the milliliter would be the amount of sodium hydroxide you put into the.
Yes. So that's the milliliter, that's the volume in milliliter of the added sodium oxide.
Okay.
And that's their behavior of the acidity that remains in the beaker. Because as you keep adding the sodium oxide, the acidity in the beaker will slow down, become less and less because the proton become less available.
Yeah.
Because you neutralize those initial protons with added hydroxide.
Yeah.
So let me keep that point. So far, I'm down to 7 milliliters. So 7 milliliters been added. So 7.0. Okay. Now let me add. So I guess that could be a damage in milliliter. Let me add a milliliter. Let me see the chance of seeing a number as close as 6. So now I'm slowing down. So I'm adding maybe dropwise, but then here's the He's almost 8. Let me just complete that as exactly 8. Okay, so this is just about 8. Okay, so now I can see something occurring. See that jump? See that point right there? So there's a good amount of jump, but I keep on jumping faster and faster and faster up until around 6. One start at around 5.5 to 6, and even though maybe a single droplet, maybe half a droplet, maybe just a faint, maybe a little fraction of a droplet, you add it to that solution, you flip it into pink, and the number will spike between 6 to 11 to 12 on its own. But so far, we're not inside that danger zone. Let me read that volume. So it says 8. So let me just keep that number. So I'm going to hit that dial keep and record 8.00. And then I'm going to add, so let me add half a milliliter. Okay, so I'm going to add half a milliliter. Right there. See that pink color? Let's hope it disappears. It did. Okay, but I'm getting a little bit more anxious because that color is telling me one thing. I'm getting a little bit closer to the endpoint. So I perhaps added good amount of hydroxide based on the initial number of the protons and almost getting closer and closer to the matching number of the added hydroxide to the initial number of the protons. And here's the number showing it because that number starts to increase on its own rapidly. So I'm going to start, be careful with the addition. Now I'm going to slow down the addition. Instead of adding a milliliter or half a milliliter, I'm going to start adding a few drops. Maybe 0.1 milliliter, maybe 0.2 milliliter, maybe 1 or 2 drops up until I achieve the results, which is a pink color. Let me give you the reading. So it says here 8.50. So the down or the amount of volume is 8.50. But notice we're getting closer. So this is just about 5. Okay, the real extreme danger zone is 6. 6 is an ultimate as far as the values. So if you add maybe half a droplet or a tiny fraction of it or hardly anything, eventually it's going to spike on its own. So now let me add maybe 1 or 2 droplets. Let me see the effect of adding. Here's 1 droplet. Okay, let's wait. See that background? See that background? So let me add, but you see that number. So I'm onto that pH value. Let me add a second droplet. You can see that background turning pink, but I want that pink color to show throughout the solution for at least 30 seconds. Not yet there, but let me add a third drop. Okay, is it pink yet? It fades away. It's gone. Now let me add. All right, so now I'm gonna just let me record that number. Even though it's not the endpoint, you see how that color fades away, disappeared. Let me record that number. Okay, so I want to record the volume on that burette. So right now I have 8 point. So let's say this is 8.75. So I've added 8.75. So keep 8.75. All right. All right. So, but notice the values. We're inside the danger zone of the addition. So I guess I'm going to add 1 drop and wait, 1 drop and wait. So let's add 1 drop and wait. Here's 1 drop. Okay. That pink color disappeared. All right. So I guess I'll add another drop, then record the volume. Okay. All right, so let me add, let me see. All right. So we're just about 8.9. So I guess, let me record that number. So the volume is 8.9. So keep 8.90. All right. So now I want to add another drop. Maybe another drop. And I'll wait. So not there yet, because that bin color appears and disappears. It takes about 3 seconds for it to stay in the solution. Then it'll fade away, it'll disappear. Only then it'll be considered as the endpoint. Not there yet. So I see that color stays maybe for like maybe 4 or 5 seconds, but it disappears. Let me record that number. So I see 9. I'm going to record that number as 9. So keep that volume as 9. So this is 9.0. All right. So now, as I said earlier, so when the BH when you enter the BH values of 6 and beyond, it becomes extremely delicate. So now I want to add very, very delicate amounts of one drop, one at a time. Is one drop. Let's count. So as you see that bin color count to 30. Did it stay in solution for 30 seconds? Maybe. Did it stay for 30 seconds?
It ended up being there for like about 10 to 12 seconds.
Okay, but not yet 30. Okay, let's record that number. So right now, it's on one drop. Okay, didn't do much damage in here, but I see, let's say 9.05, not even 9.1. All right, so let me add the second drop. And I'll wait. This is the addition of one drop. One drop. So keep counting. That looks like it. Agree?
Yes.
Yeah. So that bin
Agree.
color remains in the solution. Yeah. So the bingish background. Okay. So that's the bingish background. Yeah. And it remains. Okay. So this is your endpoint. Let me record that value. So it occurred by the addition of 9.1. So right now I have, so the volume to be cut is 9.10. So now I want to add, so now I'm at the endpoint because I've seen that color stays in solution. But I want to add now one drop. So now I want to go shy away. So I'm going to run away from that endpoint because I already achieved the endpoint. Most likely based on that color appears in solution as pink, it means the amount of proton now equal, number-wise, the amount of added hydroxide. They're equal. I want to spike it in such a way as the amount of added hydroxide a little bit more. Okay, for a reason, based on that software, I need to keep adding until it becomes deep pink. But right now we achieved the endpoint, which is when we added like 9.1 milliliter of the acid. Makes sense? But now I'm going to just add purposely extra amount of the base. Okay, because in order to visualize what's going on using the software, so I need to add more base. So I want to approach it by just slightly adding, here's 2 drops. And now it becomes pinkish color that would stay in solution. That color would not fade away, would not do anything. It'll stay in solution. And I hardly added 2 drops. All right. So let's record that volume. So it says here, so this is 9.2. So this is 9.2. So keep that volume to 9.25 roughly. All right, let's see that number. Okay, let's hold on for a second. Let's see if that number is going to go on its own. Sometimes it'll decide to go on its own. Okay, so for example, so you see that droplets? There's droplets of the acid of the base hanging on that burette nozzle. So I just wash it down. Let's see if that droplet at the tip of the nozzle, I just rinsed it down. Let's see if that's gonna do the damage. So remember, like either 1 droplet or half a droplet, quarter of droplets, or even fraction of 1 droplet, maybe 100 times fraction of that droplet, is sufficient to spike that number to maybe to say 10 or 11. Let's see. Let's wait until that number stabilizes. Let's see what's gonna happen. So it keeps on going. Let's see. So within a minute, if it doesn't change, if that digit, if that 10th placeholder, that number 2, that digit 2, if it doesn't change, and within a minute, we can stop the collection and say keep it. But it seems to be not the case. So noting that 2 is going to flip into 3. Let's see if that 3 is going to hold. So count for 60 seconds, see that 3 is going to hold. It didn't. Okay, so I'm gonna just, just wait on it. I'm gonna wait until that number is stopped and stabilized. It's not stabilizing. And notice what's going on the screen. Follow that droplets. Follow that pH value. It's moving up by itself on its own. I did not add anything. I stopped adding anything, but that point keeps on moving up and up by itself. And here's the value showing it. So mount to that point. So now I'm going to keep that cursor next to it and see how that is going to move up on its own. It did.
It seems that the pH increases by 0.01 approximately every 2 seconds.
Yeah. Let's see where that number is going to end up. Yeah, so we need to be patient and see exactly where that spike is going to occur, because it's as if we're observing it and it's occurring on its own. It's occurring on its own, don't touch it. Just let it do its own business. Because keep it on spiking, increasing on its own by itself. Just watch it. The minute you see the values and the digits are not moving, are not changing, especially that decimal value, the first decimal value, if it maintains itself within a minute, not changing, so you can stop it and keep it. But I don't see it, so I see it continue changing, and within a minute or less. So now 9 is approaching. Yep, 7.9. All right, so 7.94. All right, so flip to 8. All right, so any questions so far?
So what do we do after we just, reach the, after we go beyond the, after we're just, waiting? So I'm just wondering what we're doing next after just the,
So
trying
the
to,
next step basically is I'm going to continue adding the sodium oxide until I see the pH value in within maybe 12, 12 and a half, 13. That value can go higher still, but then I'll stop at around maybe 12 and a half, 13. So I'm building what's known as an S shape. So that plot, that curve, so start as like almost straight line, and then it's gonna spike, it's gonna increase, and on to build the second flat line. Once I see the second feature, which is another flat line that will occur later on upon addition of extra amount of base. Once I see that, I'll stop the processing of the data, and the data is complete to be processed, to be analyzed.
yeah.
Stop it till I see a second straight line that would show on this side.
Oh yeah. And so yeah. I'm also just wondering like if we should just when we just do the recordings on the titration sheet.
So for the titration sheet, so far we have the following. So all we have basically is so we have so we can record the volume of hydrochloric acid for the first trial. Remember that volume? So record that as 10.00.
10.001
milliliters. So that's the volume. So let's record 10.00, the volume of sodium hydroxide. Okay.
Okay.
And then so we record the molarity of the sodium hydroxide to be 0.1005.
Yeah, I can remember that value just on one of the containers.
Right.
That was sort of
So
what.
now the initial volume of sodium oxide inside the burette, it was at 0 dial, because I filled it to 0.00. So let's record the initial volume of sodium hydroxide inside the burette to be 0. So record that number to be 0.00. So this is what I have. Now I'm going to wait until the volume of sodium hydroxide been added until the endpoint. So that is to be materialized, to be found, figured out from the software. So I'm going to wait for that software to develop that shape, which is the S shape configuration. And then I'll let the software to analyze the final volume for me. So no longer visual. So do I still need that color to be shown or to be developing, or do I still need to add any droplets of that visual phenolphthalein thing? No. Because the software and the electronics operates in a different route, in a totally different way of looking at the data. It's looking, it sees the proton. So that probe basically is sniffing out the counts of the protons. The less of the number of the protons available in solution, the higher the pH value based on that probe sensor. Eventually, when the numbers start to go far exceed the 7, so 7 basically is, it means the amount of protons matching the amount of added hydroxide, beyond which any added sodium oxide becomes like a sheer extra stuff, not needed. And the sensor basically is telling us that number based on a higher value than 7. But 7 basically is a mid-range, indicating the neutrality. The amount of added acid to the base is the same. And this is true only for the addition of strong acid to a strong base. Sodium oxide is a strong base. Hydrochloric acid is strong acid. Every time you add strong acid to a strong base, the neutral, the mid-range, the midpoint between them, which is neutral, the same as drinking water. Neutral pH value is 7. But if you come in with a weak acid and strong base, or weak base and strong acid, the midpoint where the amount of acid and the base are equivalent is not at 7. Okay, but this is a topic of chemistry 140, which is general chemistry 2. So in general chemistry 1, we'll show you maybe bits and pieces of the pH value, but we'll continue for showing more in chemistry 140. All right, so it looks like, is it stable? I guess, yeah, it's, did it move faster? I guess kind of slowed down a bit. So I guess, let's see that number, just to verify. Yeah, that number remains to be the same. Okay, 9.10, did not move. All right, let me just add maybe a few drops. So I guess 1 or 2 drops would not hurt. Squeeze 1 drop, to see the effect of 1 drop. Second drop. All right, let me just read that volume. So now it says 9.35. All right, so and within a minute, if that digit does not move drastically, I'm gonna record that as 9.35. So let's see, so start with 9.2, and let's just count for 60 seconds. So now count. So we should be good, all right? So I guess we should be good. So we can just keep that value to be 9.35. All right, so let me add 2 drops. 1, 2, maybe 3. So let's go into that digit. Let's see if that changes. So it should be good. Yeah, it's not really moving drastically. So I'm going to keep that value to read 9.55. All right, so I'm going to add maybe 3 more drops. 1, 2, 3. So as I start to go shy away from that jump, so here's the jump as if jump is pretty much that sizable jump occurred already. So now later on addition will move the pH up slightly, but would not move it drastically. I'll continue adding the sodium oxide up until I see somewhere around maybe 12, 12 and a half, and then I'll stop. All right, so as we go there, value looks like it slows down. So right now it is 9.7. Just accept that value as 9.7. All right, so let me add a few more drops. And the volume would say, so this is 9.9 so far. So I guess I'll accept that value as, so this is 9.9. Then I'll add maybe, so now I'll be adding maybe like 5 drops. I'm not going to do with somebody. Now it's 10.2. All right. Let me record that number. So this is 10.20. Let me add a few more drops. So now I can comfortably start to add maybe like 20 drops. Roughly 15 to 20 drops is a milliliter. So I can add maybe 5, 10 drops, or maybe half a milliliter, and so on. So now I can fly off a little bit quicker. So it says here 10.50. And knowing that decimal value 8, basically the 8 over 10 placeholder, 10th placeholder, it's not really moving drastically. It is moving, but then very slowly. So I can just accept that value. So once again, this value is 10.50. So this is 10.50 milliliter. Let me add another half a milliliter. So this is 11. So keep an eye on that digit. So far we're at 11 milliliter addition. looks like we're good, right? So I'm gonna keep that 11, 11.00. And so let me add another milliliter. I'll make it 12. So he's a 4. Not bad. All right, so it's hardly moving. So this is 12, 12.00. All right, so now I'm gonna add another milliliter. So make it 13, 1 scoop. So here's the second blood to start developing, second straight line, similar to the beginning, okay, but that occurs after the spike in the middle. So right now I'm at 13. All right, looks like it's not moving. So 13, 13.00. Okay, so move on to maybe 14, and then the flat line becomes aberrant because I want to develop it in a full sense of a straight line. So we've added 14 so far. Move on to the 7. Okay, so we can accept the 14, 14.0. Let's add 15. All right, should be good. So 15.0. Okay, so and then I guess I can add 16. All right, so noting how that straight line start to develop, okay, and then I can go add a little bit more quicker, okay. But so far I'm at 16 addition, and that they're just sort of very stable. So this is 16. And then 17. All right, so here's my 12, okay, which is good result. So this is 17. So I can add maybe another, just for the sake of fun, I guess I can add like 2 milliliter in 1 scoop down to 19. Okay, so I delivered 19 milliliter. Nothing's gonna occur drastic. So 12 remains to be almost 12, solid, means the straight line is developed. So far I'm at 19 milliliter. Okay, let me just add that value and I'll stop the collection. Okay, so this is my second straight line been developing. Here's the first initial straight line. Here's the jump. Here's the second straight line, and I'll stop the addition. So the data collection is stopped and ready to analyze. Okay, let me shuffle these on the side. And now let me just dismantle that setup. All right. So now let's analyze the data, and we should be all set. All right. So now to analyze the data, okay, I just want to show it to you how easily it can be analyzed. So from that software, what you need basically is toggle. So here's the arrow. So, so inside that box, it says page 1. So click twice. So here's the first click. Here's the second page. Here's the third one. So looking at the crossing of that blue curve. So the crossing of that blue curve, crossing the x-axis, and read the value. Okay, so that blue curve, see the curve? So that blue curve. So what I've done basically is I went to that software and just clicked twice on that arrow and shown the third page, it says on it page 3, and just read that crossing point, the value on the x-axis at the crossing, what seems to be the value on the x-axis. So read those numbers. So can you see at the bottom screen? So at the lower left screen, so at the lower left, let me just mask it so it would not be. All right, so here's the graph. So read on that lower end. So here's a box. If I hover inside the plot area, there'll be coordinates of x and y values. Read me the x value. The x values are in milliliter. So here's so here's the hair across the cursor.
It's
Here's the cursor.
9.4.
All right, so can you see it more clear? So this is, I see 9.300.
Oh, I also see that crossing value is 9.3 as well.
9 point. So let's record that number. So that's the final volume when the perfect match between the last proton reacted with the last added OH as one proton to one OH, 1 on 1. Yeah, so this software basically nails down the last grain of the accuracy of the OHs and added to that proton and equate the two, which is the crossing of that blue line crossing the x-axis. It crossed it at 9 point, so record that number. Okay, so that's the value. Let me just stop that. So I'm gonna record that number. So the crossing occurred at 9.300. Okay, and I have four sig figs, which will allow with good amount of accuracy. So now, what's the difference? What's the difference in the volume? That's the volume being consumed into reaching to the endpoint. So the volume of sodium oxide added at the equivalent point is 9.300. So I'm gonna write down that number. Okay, so that's how accurate it can get. Okay, so now how do you figure out the molarity of the hydrochloric acid unknown? Okay, so here's your first child 1 calculation. Okay, so let me show it on the screen. So let me erase that part. So far what we have. So we have the following information so far. We know the molarity of the added sodium oxide. We know how much it took to reach the equivalent point. We know the volume of the acid been titrated. What's left to find? The molarity of the unknown. So every time you have a titration, so we have moles of the protons initially in the beaker at the equivalent point should be the same as the moles of the OH. All right, so what we know about the acid, the moles of proton, what we know is the volume, which is, doesn't matter if I keep it in liters or milliliter, right? Doesn't matter, because on the other side, I could do the same if I kept that volume in milliliter. I can keep the other volume of the sodium hydroxide milliliter. It doesn't matter. Okay, but let's move on and convert to liter, which is, I guess, the best bet as far as the unit. Let's say we've added, what was the initial amount of the acid been added to that beaker? 10 milliliter. Okay, so 10 milliliter. And then convert that volume to liter. So a liter has in it 1,000 milliliter. So that's the volume of the acid been added. Multiply that volume, that's the volume, times the molarity of the acid, which is we don't know, which is unknown. Okay, that moles of the proton. So these multiplication represents the moles of proton of or found inside the 10 milliliter beaker. That should be equivalent to the moles of sodium hydroxide, which is known. Okay, so I define the moles of sodium hydroxide been added. We've utilized 9.3 at the equivalent point. So 9.3, the volume of the sodium hydroxide, 9.300, look at the accuracy, milliliter of sodium hydroxide been utilized, and convert that number to liter, volume of liter. A liter has in it 1,000 milliliter. And then multiply that volume by the molarity of the bottle, and the molarity says on the bottle 0.1005 molar. So that's the part for the sodium hydroxide. So this is sodium hydroxide, and that part is the hydrochloric acid unknown. Okay, so the moles of the proton should equal the moles of hydroxides from that initial definition. Eventually, the only unknown remains is the molarity of the acid. So that's the molarity of the acid, hydrochloric acid. So divide by that volume. So in here, so what's left basically is, so if you divide by 1,000, that would give you 9.0093 liter. Agree? And then multiply this by 0. The molarity of the sodium oxide, 0.005. All these numbers to be divided by the volume in liter of 10 milliliter, which is 0.01, 0.010. So 10 milliliter basically, but I measured it with 10.00. So I'm gonna carry over all these zeros. And that's my precisions. Okay, and that number basically has in it how many zeros after the 3? 2 more zeros. So I'm gonna carry them over. Because if you want to look at them in the precision, that's your precision. True? So that's your precision. Times it by that number. So 0.009300 and 0.1005 and then 0.01000. Well, what's the precision so far? 4 sigfig in that multiplication division. Okay, so multiply, divide, let me know what's that number. The 4 sigfigs.
It's going to be 0.09347.
Excellent. All right, you see that? All right, so we're able to generate something that is extremely exotic as far as the precision, as far as the showing the sigfig. Because you have to show 4 sigfigs based on those measurements, true? And that number shows it, okay? If you've done it manual calculation, there's no way to come up with that precision. The starting point is somewhere around maybe 3. You can't record that number higher than that 3 or better than that 3. So you're missing out those more precise values. Okay, so that's the bottle molarity. That's the acid molarity. That's precisely what's in that bottle. So what's inside that bottle, you nail it down to 4 sigfig precision accuracy of the bottle concentration. Okay, so that's your way of figuring that out of unknown bottle of hydrochloric acid. So the same goes for the second trial, third trial. We'll take until maybe midnight to perform both and to finalize them. So I'll provide those information for you separately, and as a folder that has the trial 1, trial 2, and trial 3. So complete the analysis. Remember the way exactly what we've done here to figure out the molarity of the first trial for that unknown hydrochloric acid. Do the same to figure out the molarity of the unknown for the second trial and for the third trial in the same way. Add them up and divide it by 3. That's the average. And submit the lab report. So the lab report turns out to be like a very, very straightforward. Okay, so it turns out to be so much fun as far as the lab report. Okay. Any question about how to finish the lab report?
For the for the acid base titration sheet, I should just I would submit the PDF that you show in the Canvas shell.
Right. So very soon I'm going to just come up with the second trial and third trial, and then just figure out the molarity of the hydrochloric acid based on the second trial and the third trial. That's what's left following the first trial value. Add them up, divided by 3. That's their average.
Yeah, and so let's see. So to do the calculations for the unknown acid, I would just use a balanced equation for it.
It's already been done. So as far as the equation, there's nothing to be balanced or anything. It's already 1-to-1. So I've shown you that this reaction is a 1-to-1. There's nothing to be done. Beyond which, so similar to the first column that says trial 1. So those numbers, the way we attempt to figure out the unknown molarity of the acid based on those input, based on those first column trial 1 input, use the second trial input and mimic exactly what we did to figure out the molarity of the unknown for the second trial, and do the same for the third trial.
Yeah. So I would just submit that sheet that you have here on to you.
Yeah, and redo. We're going to show me one more time, even though we've done it together as in group, the trial 1 molarity of the unknown acid. So show it to me one more time and show me exactly a replica of the calculation for the second trial and for the third trial, and the average. So don't say just like here's the value. Trust me. So here's the value. So I would not take it as you've done something. Show me the work.
Yeah.
Because what's left is just like 2 tiny calculations.
Yep. Yeah.
Professor.
And you're done. This is it. So your whole lab report of experiment 11 basically is just that sheet. Okay. Any question? Any other concerns or anything? I'll back you up with the data, with the full data for trial 2 and 3.
Oh yeah. So let's see. So the data points I took down on the lab manual would be that the moles of hydrogen ions in trial 1 is 0.1500. Then the moles.
Yeah, I would not look back at the full blown lab manual procedure and data sheet, because it'd be confusing to follow exactly what they're trying to say and trying to. So do not pile up whatever that requires. Don't look back at that lab report sheet on what to put in here, what to put there. Don't give me that sheet, because it's not following exactly what we've done. What we've done is electronic collection of the data versus manual. So this requires manual collection of data.
Yeah, so I would just not need to worry about the sheet that's in the lab.
Right. Just submit this sheet, fill it out,
Professor.
show me the calculation, submit that sheet only.
Could you go ahead and put that closer to the camera? It's really hard to see.
So if you didn't follow these down, you just easy.
So to clarify, where do we get the values for trials 2 and 3?
2 and 3, I'll provide them very soon.
Oh, okay.
I'll
So
provide
like
them to you.
last time when you gave us the missing
Right.
mass?
Exactly.
Okay.
So just make sure the calculation is, you're clear about how to approach them and how to do it on your own for trial 2 and 3. Okay, so just to replicate exactly what we done here for trial one. Any other questions?
Okay, so the formula that I would use to calculate the molarity of the unknown solution, I would just use M1, which is molarity 1 times the first volume is equal to the second molarity times second volume.
Exactly. So we came across early on while studying Chem 120, basically. Do you remember that formula, M1 times V1
Yeah. Mhm.
equals M2? Remember what was it? What's the use for that formula?
Let's see, this would often be used in
This is a dilution formula.
like the dilution, yeah.
Okay, so we use that formula to dilute solutions. So if you have concentrated solution, you want to dilute less concentrated solution. So we use that M1 V1 equals M2 V2.
Yeah.
Well, it is the same for the case of 1-to-1 mole. So just be careful. If you happen to react, since our reaction involves 1 mole of the acid, remember the reaction? So the reaction is 1 mole of the proton reacting with a mole of the hydroxide. So it's a 1-to-1.
Yeah.
And that produces water molecules.
Yeah.
But looking at that reaction, it's a 1-to-1 ratio.
Yeah. So the equation is just
So that becomes your backbone. Yeah. So if the reaction between the acid and base is 1-to-1, 1 mole of the acid reacts only with 1 mole of the base, this is the way to start.
Yeah.
Similar to dilution reaction, but there's no dilution, there's an actual reaction, but then I'm using, that becomes vital and applicable for this case of a 1-to-1 acid and base. But if you have, let's say 2 moles of the acid reacted with a mole of base, or 2 moles of base reacted with the mole of acid, assuming, for example, on the side, assuming I have H2SO4 is the acid, look what's going to happen. So here's my acid, but I'm reacting this acid with the same base, sodium hydroxide.
Mhm.
Is that a 1-to-1 mole?
Oh, in that case, it would not be a 1-to-1 because
Yeah, that would not be 1-to-1. So this
because
is
in that
sodium
case, due to the conservation of
sulfate.
mass and as a result, I would just, have to do some
So, yeah,
more
so
complicated
since
bulk.
that reaction is not 1-to-1, watch out. Do not use that dilution equation as a valid case, as a valid starting point. Do not use it.
Yeah.
So this is only utilized and used at a specific condition if you have a mole of the acid reacting with a mole of base. If you verify that this is a 1-to-1 addition, a reaction, it becomes applicable and valid.
Yeah.
Otherwise,
So M1 V1 equals M2 V2 should pretty much only work with
1-to-1.
1-to-1 ratio.
Absolutely. All right.
Thank you.
Sure. Any other question? All right. So you guys, do you guys submit the last week lab report?
Lab 10, right?
Lab 10, right?
Yes, I submitted that one.
Okay. So just make
Yeah,
sure.
I was at least able to submit it as well.
All right. Any other question? So you guys, so we still have one more lab. Okay, so I guess the last one is about enthalpy and heat, which is, I'll show you the same. I show you demo, and then you calculate one based on the demo. Okay, it should be straightforward as far as the calculation. All right, so the last two experiments, even though they look like humongous and lengthy, but then the approach is straightforward and simple. I hope you agree. Any question? Any last question? So guys, have a great night, and we'll see you next week.
I'll see you next Monday, Professor.